Hi everyone, so we've been doing plenty of problems so far, and you've found that we've needed to use the quadratic equation solver on your calculator several times. And so now that we've gone through this process multiple times, I want to talk about some shortcuts to kind of jump from the word problem, maybe past part of the ICE table, to get you closer to getting a result around pH. And then I also want to talk to you about a 5% rule, which will allow you to bypass using the quadratic equation solver in some instances. So hopefully you've seen some of those patterns in our calculation. Generally we're asked a question, what is the pH? They give us some concentration of a solution, they give us some chemical that's dissociating, and they give us a Ka or a Kb depending upon what's dissociating. So if it's something like an acid, then maybe we have a 0.5 molar solution of our acid. If it's an acid like acetic acid, CH3COOH, they're going to give us a Ka, in that case, associated with it. So we've seen this general pH type question several times, and our general response was to go ahead and do an ICE table. Generally, that equation for an acid has been HA plus H2O is in equilibrium, which H3O ions, and then that counter ion, that A minus. So we would next do an ICE table for this, and in that ICE table, the starting concentration of our acid would be that concentration of the solution that we started with in the word problem. We wouldn't do anything with the water column. We would have 0 initially of both the hydronium ions and that counter ion. We would proceed to the right, so we're going to subtract reactants and add products. And so our equilibrium line was going to be that concentration of the solution starting, 0.5 minus X, and our H3O plus was going to just be X, and this was X. So this problem would have given us some Ka. Say it's Ka equals 2.1 times 10 to the minus 5. And this is definitely not the Ka for acetic acid, but it's just the number they would give us. So the next thing we would want to do from here would be to take that Ka, say great, it's got a value associated with it, 2.1 times 10 to the minus 5. And then we would say that's going to be equal to our equilibrium expression. Our equilibrium expression is going to be X times X, and we would end up with the reactant, that 0.5 minus X, on the bottom. So we would actually have to use the quadratic equation in order to solve this problem, but it took us a long time just to get to this point. But really what we need is not the ICE table for this. Now that we've done this a couple times, we see that general pattern. What we need is this question, the information that's in the question, like the concentration of the acid, the identity of the acid, the Ka of the acid, and we should be able to jump straight down here. The Ka is going to go over here, 2.1 times 10 to the minus 5. It's going to be equal to that starting concentration, 0.5 minus X on the bottom and X squared on the top. So by recognizing this general pattern, we've actually been able to forget about that ICE table. We've been able to jump ahead. So that is a shortcut. When we're dealing with weak acids and weak bases, we should be able to jump straight ahead, because we know if we're just starting from an initial point where all you have is the reactant and 0 of the product, you're going to end up at this same point here at the end, which is going to be that equation that has to be solved with the quadratic equation solver. So let's do a couple examples where we just jump ahead. So if we have a problem that's asking us the pH of a 0.15 molar solution of some acid, we should be able to say, great, this is going to be Ka equals 2.5 times 10 to the minus 5 equals X squared over that starting concentration minus X. Okay, so we just skip the ICE table completely because this follows the general strategy that we've been employing in order to get to the pH. So now what we'd have to do is we'd have to solve for X. X would go back into the ICE table. It's really just going to be that number, whatever X equals. we're going to take the negative log of that number, and so that was going to give us the pH. So once we get that x from our quadratic equation solver, then we get the pH by taking the negative log of that number. So let's do the second example. What's the pH of a 1.05 molar solution of HF? We know that that is going to be a weak acid, and they've given us a dissociation constant that should also make us think it's in the weak range. So we're just going to jump ahead. Ka equals 6.4 times 10 to the minus 4. That's going to equal x squared. That is going to be 1.05 minus x. And so we've just cut to the chase. You're going to solve for x with a quadratic equation solver, and then you're going to get the pH by taking the negative log of whatever that answer was. Okay, so this is a shortcut to bypass the ICE table for these specific types of problems. So in both of the examples I just talked about, we solved for x using the quadratic equation. So up here, we had to solve using the quadratic equation. Once we got to this x squared, x, and a number, again, we set that equal to 0. We use the quadratic equation to solve that. So that's not very exciting. So we've got some sad faces here, because that's a pretty time-consuming process, even if you already have it in your calculator. So what is one more shortcut that we could potentially use to speed up this process? So that shortcut is the 5% rule. So it turns out there's about 5% error in all those Ka and Kb values that we've been referring to in Appendix H and Appendix I. So there's already built in some error there. So if the calculation that you're doing is also in that 5% error range, we're going to call that acceptable for what we're doing. So if we're going to apply this 5% rule, we need to make sure several conditions are in place. We need to make sure that we're talking about a weak acid and a weak base system, right? So that only a little bit of stuff is going to dissociate. That small Ka or Kb, and when I say small, I'm talking about times 10 to, the minus 6, or times 10 to the minus 10. So these really small numbers, those small Kas or Kbs, mean that very small amounts of that starting reactant are going to dissociate. So not much dissociates at all when you have a Ka or Kb that's really small. So if that occurs, if a Ka is really small, then when we solve our ICE table, when we get down to the shortcut that we just jumped to, x squared over the starting concentration minus x, if very little x dissociates, then what that means is that Ka is actually approximately equal to x squared over the starting concentration. So if you had a starting concentration of 0.5 molar and very little 0.5 molar dissociates, then that means that the concentration at the end is still very close to 0.5 molar. And so all they did was they took out this minus x term. You don't see it here. They took out that minus x term because not much of the acid actually dissociated. And if we do that, if we make that assumption, then you no longer need the quadratic equation, because you no longer have an x squared, an x, and a number. Now all we have is a number on the Ka, we have an x squared, and we have another number down here for the solution. And so you can solve that. We multiply both sides by the concentration of the starting solution, we get all numbers on the left, we take the square root, we get the value of x, good to go. Now there is one caveat. We do need to make sure that we check the percent ionization. This shortcut only works if the ionization is less than 5%. If we're above 5%, then we're in this dangerous territory where we're making assumptions that we shouldn't be. But if it's less than 5%, then we're in kind of that Goldilocks zone, and we can continue with a shortcut that really shortens how long this problem takes. So let me get into some more details of this. On the next slide, we'll talk again in generalities, but we'll actually show you some numbers more than just kind of these bullets here, and then we'll do 2 examples to hopefully really drive home when you can use the 5% rule and when you cannot use the 5% rule. So in general terms, we said we have, for our problems, that were asking us to solve for the pH or the concentration of H3O or what have you, that we have this general formula for an acid combining with water is going to form those hydronium ions and the conjugate base, right? So we've got this general formula, and so if there's a Ka that is associated with this acid, if there's some Ka equals a number, we can think about what that number means. If the Ka is close to 1, so say, 1 times 10 to the minus 1, or 1 times 10 to the 0, which would just be 1, then that means that a lot of the HA, a lot of that acid, is going to dissociate. So that means we're going to end up with a lot of H3O. But if instead we have a Ka value that's really small, 1 times 10 to the minus 5, or 1 times 10 to the minus 10, some really small number, then that means that almost none of this HA turned into H3O+. So when we do our ice table, we would start off with some initial concentration of the acid, so the brackets meaning concentration of this acid at time 0. We'd have nothing for the H2O column. We would have 0 of both the products. We would end up subtracting some reactant, making some product. We would end up with that concentration HA at time 0 minus X, and then this would just be X, and this would be X. And so when we think about this, if the Ka is really small, that means that not much left the HA. So this term over here is getting to be equivalent to HA. So if HA minus X, if that X is super, super small, then HA minus X is pretty much the same as HAX. And so we can write that out as a statement. If the Ka is really small, then HA minus X is approximately equal to HA. So that means when we get to trying to do the solving part of this, that x squared over HA minus X is now approximately equal to x squared over HA, right? Because there's not going to be a very big change in HA, we just treat it like it's still that HA number. And now when we set this equal to Ka, which is a number, we no longer need the quadratic equation solver because we don't have an x squared and an x and a number. Now we just have an x squared and numbers. We can get all the numbers on one side by multiplying both sides by the HA concentration at time 0, and then we can just take the square root of both sides. We can end up with x being the square root of whatever that number was after you multiplied it together. And then as that final step, what we want to do is we want to check the percent ionization to make sure it falls into that 5% category. We're going to take that x value, we're going to divide it by the starting concentration of HA. So we're saying how much x, how much dissociated out of that starting amount, and of course we multiply this by 100 so that we can get our percent, and then whatever number that equals, if less than 5%, we're good to go. If that number gives us something that is greater than 5%, well, sad day, we have to go back and do the quadratic equation. So I will say that in the homework set, there are problems that specifically say something 5% in the title, and it's saying that it's expecting you're going to use the 5% rule in order to come up with the answers, rather than using the quadratic equation solver. So now that we've talked in very general terms, let's go ahead and do a couple problems, one which will demonstrate when we can use the 5% rule, and one which will demonstrate when we cannot use the 5% rule. And we're going to use the examples that we already used for the shortcuts a couple slides ago. So we just said we could cut to the chase if we knew we were looking for the pH of a 0.15 molar solution of this acid given the Ka. So I'm just going to go ahead and jump ahead to the starting point. Alright, so that was my first shortcut, right? I go directly to the number for Ka equals x squared over the starting concentration minus x. And so the next step for me is going to be to make the 5% rule assumption and turn that 0.15 minus x into just 0.15. So now I've written that out, and I can go ahead and solve for x. I'm going to get x squared by itself on one side, and then I'm going to take the square root of both sides, and I get a value of x as 1.9 times 10 to the minus 3, trying to keep track of my sig figs with just 2 sig figs. So now I have that value of x. I need to go in and I need to check to make sure I'm obeying the 5% assumption. That means I'm checking the percent ionization. Percent ionization is going to be that fraction that ionized and formed hydronium ions divided by the starting concentration of the acid times 100. So I'm going to go ahead and plug in the 1.9 times 10 to the minus 3 that we just solved for, the 0.15 molar, which was the starting concentration of our acid. I'm going to multiply that by 100. My calculator helps me decide that I have a percent ionization of 1.3%. 1.3 is definitely less than 5%, so I'm good to go with this assumption. I did not have to use the quadratic equation. I could have just made this assumption that not very much of this acid was going to dissociate. So now that means that I can proceed with calculating my pH, which is what they were actually asking me about. What is the pH of the solution? So let me go ahead and take the negative log of my H3O concentration, which in this case is the negative log of that x value that I had, 1.9 times 10 to the minus 3, and the pH that I get is going to be 2.7. So definitely still an acidic solution. It's just a weak acid because not a lot of it actually ionized to go into solution. So this would be the way for me to use a couple of my shortcuts. I jumped past the ice table because I know already what it's going to look like when I get down to that equilibrium expression. I made the assumption of 5% or less dissociated. That let me bypass using the quadratic equation. I checked it, I'm able to use it, and then I went forward with trying to calculate the pH. Now let's work an example where the 5% rule does not apply. So let me go ahead and jump ahead just like we previously did. I'm able to jump past the ice table. I'm able to take that Ka value, set it equal to x squared over the starting concentration minus x. I recognize that that is something that would need to use a quadratic equation solver in order to solve for x. So I want to make an assumption that I can just go ahead and assume less than 5% ionizes to bypass the need to use that quadratic equation solver. So assuming the 5% rule applies, I just took that 1.05 minus x and turned it into a 1.05. Now I don't have to use the quadratic equation solver because I just have an x squared in numbers. I can go ahead and start to solve for x. I can take the square root of both sides, and my x is going to be equal to 0.26. So I've solved for an x using the assumption, but now I need to check that assumption. I check that assumption with percent ionization, which is going to be my 0.26 that I just solved for over the starting concentration, 1.05. I'm going to multiply that answer by 100 to get into a percent, and when I do that, and round for sig figs, I end up with 25%. And so you probably could have eyeballed that. 0.25 over 1 is around a quarter, right? So we got around 25% ionization. So that unfortunately means that we're not going to be able to use the 5% rule on this one. So I think it was still worth the time to see if we could do it. But now that we see that we cannot do it, we're going to have to solve for x by doing it the old-fashioned way with the quadratic equation. So we're just going to kind of scratch out what we've already done and then go back up to this blue step and start simplifying like we've done before. We have to do multiplication by both sides. We have to distribute this number to the number and the minus x. We end up with numbers and x's and x squareds. We're all going to set this equal to 0. Now you've got your ax formula. You're going to put that into the quadratic equation or put it into your calculator to solve for the x. And then once you have your x, we still remember that we've kind of bypassed the ice table. So now when you solve for x, you're just going to take the negative log of whatever that x value is, the one that's appropriate for your ice table, the one that doesn't give you a negative concentration, and that's the way you would get your pH. But we've done that already, and the point of this was to teach you the shortcuts and what we're talking about when we talk about the 5% rule. So hopefully this will speed up some of the calculations for you and make it a little bit more sense in the homework assignment where you see headings that are referring to 5%.